hope you're doing well. Today we're going to solve this question, minimum obstacle removal to reach the corner. So basically, I'm going to explain what this question wants us to do. So right as you can see, we have given a 2D matrix in which 0 denotes the empty space and 1 denotes this wall, this obstacle. So they want us to find a path from this starting position to ending position. I mean, it is always going to be like this. The starting position is going to be at the corner 0, 0, and the ending position is going to be the length of row -1 and the column -1. Yeah, that's basically it. So if I try to do a travel from this way, what I found out that the obstacle which I tackled in between this path was 2. And even I mean, if I try to do the same thing by using this path, I can see that I just got encountered by 3 obstacles. So which one is the minimum one? Obviously the 2. So the question wants us to return the minimum amount of obstacle required to reach the ending point. So I mean, how can we do that? I mean, in the question they have also given us to remove these obstacles. I mean, we don't actually need to remove, since we just need to pass the output as an integer. So I mean, there is no modification. I'm going to tell you the trick behind it. I mean, how can we do this? So the first idea, I mean, you must be thinking the first solution which comes into your mind would be the backtracking approach, and you will be like that, okay sir, we're simply going to start from 0 comma 0 row, and we're gonna do a breadth first search or a depth first search, and just simply going to check all the possible paths, and after that in all the possible paths we're gonna keep track of the minimum one. I mean, yeah, you kind of do the backtracking approach, but that approach is not efficient. There is a better way, which I'm gonna tell you. So if you just consider the logic of a graph algorithm, there is a one better graph algorithm which can solve this question efficiently. I mean, better than backtracking. I mean, backtracking is just kind of not optimistic. So let's say we are at this position. So at this position, I can see I have no obstacle right now. But if I try to reach at this position, I mean, we haven't reached it yet, but if we try to do, it's gonna be 1. And if I try to do the same thing again over here, it's also going to be 1. But right now, since there is a tie between these two uh, obstacles, we can either pick any of these. So once we try to reach over there, we haven't reached it that place yet, it's gonna be 2. And if we try to do the same thing right at this place, it's gonna be 2. So out of this thing we have already, I mean, let me just change the color. So as you can see right over here, if we try to do this, if we try to calculate that, we have used these two locations, or you can sell already. So we have out of these three, which one should we pick? I mean, if you are clever, you're obviously going to pick the smallest one. I mean, yeah, that could be the approach. So you must be, I mean, from now on, I mean, if you have studied the graph, you already know which kind of algorithm we are working on. So it's a Dijkstra algorithm. So in the Dijkstra algorithm, I mean, we obviously going to pick the 1. Then after that, it's gonna be 2, and it's already committed 2. Then I'm gonna pick this, any of these. Let's say I pick this, and then after that, I can see there is no obstacle, so the number is going to be not going to be changed. It's remain 2, and it's gonna be 2, and I mean, it's gonna be 3. So obviously, I'm going to pick this path, and here we are finally. And as the, I mean, if I try to run the algorithm, once we reach the end, the number which you get is always going to be the minimum. So yeah, that's pretty much it. So I'm gonna explain you the code. I mean, it will be more informative, so that's why. So I mean, as you can see, if you have noticed one thing which I was doing right at this place, that if I have used these queues, I mean, these things, these two cells already, these cells are kind of remaining. So I mean, I just need to pick up the minimum out of it. So that's why I'm gonna use a min heap. Since min heap is kind of data structure, we just keep the minimum element at the top. So it I mean, from instead of iterating all over this place, we can just simply use a min heap and just pick out the smallest one. So we don't even need to take care of that. The min heap will do it from our side. So let me just code this thing up and it will be more clear. Let's say we have row. I mean, how many row we gonna have? Row is gonna be obviously the length of the grid. So it's gonna be like this. Then after that, the column is going to be grid of oh, I mean 0. It's just gonna tell the column. The row is this and the column is this. So it's just gonna give us that value. Then after that, what we want? I mean, I just told you guys. I mean, we need a min heap, and min heap kind of just a list, and we're simply going to what? We're simply going to insert what it is, we're going to feed it with the initial values which we already know. In what do we say, in Python we have in heap like kind of like this, and we just going to tell, I mean, we don't even need to do this. I mean, wait, just yeah. So as you can see right at this place, we're gonna use min heap, and then we're gonna just push this thing up. We're gonna say heap and then push, and then I'm gonna tell, I mean, which array we should act, which array should be treated as min heap, and then we're gonna tell the value 0 comma 0 comma 0. So I mean, the first 0 basically tells the obstacle which we have approached. I mean, the number of obstacle which we're calculating right at this place. Then after that, these two column gonna tell us the location of the obstacle. I mean, where it basically resides. So it's resides at this row and at this column. Then after that, we need a visit set. Let's say we come in a situation in which we found out that we have reached the same place again. So just to avoid this thing, since we are moving in 4 direction, it is possible that once we are at this place, we could go back to this place again, And just kind of rubbish. So let me just code right over here. So let's say I'm at this place, we can go at this place and this place and this place, and it can create a loop. If you know. So that's why there should be a visit. Then after that, what we're gonna do, basically we're going to check while main heap is not empty. So if it is not empty, we're gonna pop it from the left. So we're gonna say the obstacle which we have calculated right now, and the row and column, the location of that particular obstacle, and the next thing which we have is heap queue, and then we're gonna just simply heap pop this thing out, and heap pop from which heap? From this array which is treated like a heap. The heap main heap is also known as priority queue, just for the information, if you're new to this. So and after that, what we're going to do, basically we're gonna use a directional array which is going to be like this. Instead of creating a loop, a proper loop going this, and instead of repeating code, we can just simply use this and create a loop out of it. Let me just show you. So I'm just gonna repeat again and again. So it's gonna be like downward, it's gonna be upward, and it's gonna be, let's say it's gonna be right, and this one is going to be left. Yeah, then after that, what we can do, we can just simply iterate over all the direction, one, direction two. You can also say neighbors, but I would like to call it direction. It's kind of into it. The main idea is, since we are moving in this direction, that's why I'm calling it direction. Yeah, then after that, what we're gonna do, basically, since we have reached this point, we're gonna check. We're not even going to check right now. First of all, what we're gonna do, we're just simply going to tell that add this thing to our heap, since we're gonna keep trace of the minimum value. So what does it mean? That if I'm at this place, if I have reached, the row have reached to the row minus 1, and column have reached to the column minus 1, we're simply going to return our obstacle, since the always we're going to pop out the minimum value, and that's the minimum answer which we want. So in this, we're gonna always going to add this thing. So let's say main heap is this, and after that we're gonna say obstacle plus, I'm gonna get back to the 0, it's gonna be 0 or 1. But before that, we're just going to add the direction dr and dc. Then after that, you must be thinking, when should we add 1? So you must be thinking that we should gonna create a ternary kind of operation. So if the obstacle is 1, we're gonna add 1. If it is empty, we're gonna add 0. But we don't even need to do this thing, since if we just do simply like this, a dr, and we're gonna say direction of column, it's obviously going to be do the same thing, since if it is empty, it's gonna add 0, and if it is not empty, it's gonna add 1. Then after that, what we're gonna say, okay, we have done this thing, so we have used this kind of cell already, so we're gonna add it to our visit set. So there is no point of going it over again. So since we have added it, we just want to tell that it is added, so you are not allowed to come there at this place again. So we're gonna say, if this thing is already visit, you don't need to compute anymore. So we're gonna say continue, just move on. Then after that, what we're gonna do, as you must be thinking, there must be a cause. There must be a situation if you found out that this drdc could be outer bound. Just let me just put that direction right over here. There is some kind of update issue. So yeah, it could be possible that it is outer bound. To just to make confirm that it is safe, it is inner bound, we can just put a simple condition, as you have already guessed, that dr could be less than 0, or dc also could be less than 0, or dr is greater than the row which we have, greater than equal to row, or could be dc could be greater than equal to column we have, since it is going to be outer bound. So there is no point of it. And let's say hopefully it will run. Let's just check. Okay, so that was the whole code. Hope it was more clear after coding the code. That's pretty much it.